Hello everyone, I'm Paul and today we're solving problem 3373, maximize the number of target nodes after connecting trees to. This is a hard problem and this is the second part of a problem we solved recently. The video for that one is in my channel, so I recommend you to go and watch it if you haven't. And if you were able to solve that first part, I think that you can solve this one too, or at least you can understand the solution. So now let's go with the intuition, approach, and efficient solution. We're given two undirected trees with n and m nodes. And we know that whenever we talk about undirected trees, we are talking about graphs. And we need to return an array answer where each element in the array is the maximum possible number of nodes that we can iterate from the source, meaning from that element, and where the number of edges from the source to every node is even. And we can connect one node from the first tree to another node in the second tree. Let's see what this means with an example. Let's say we have these edges. Let's say this is edges 1 and this is edges 2, and from this we can build these graphs. The result is initially an empty array, and we start here at index 0. So we start with this node, and this is the source. From here we want to know how many nodes can we add here, and if we are here we can't add this, we can't add this, but we can add this one because here we have 1, 2 edges, and 2 is an even number, so we add this node. And we also add this node because from here to here we also have 2 edges. So up to this point we have 3 nodes that we can add here. But remember, we can connect this tree with this other tree. Now the question is, should we connect 0 with 0? Should we connect this 0 with this 2? Should we connect this with the 3? What's the best choice here? So let's say we connect this 0 with this 0. This means we won't take this one because here we have only one edge, so we are not taking this one. But we are taking this one, we are taking this one, because here we have 1, 2 edges, and here we have 1, 2 edges. And we won't take this one, we will take this one, we won't take this one, we will take this and this. Okay, so finally in this index 0 we will put 3 plus 5 nodes, 8 nodes in total. And now if you were paying attention, you might have realized that here we have all the information we need to solve this, because in this right graph we already have the 2 groups of nodes that we need. We know that one group has a 0, a 7, and a 4, this, and this, and the other group has a 2, a 3, a 1, a 5, and a 6. So we have one group with 3 elements and another group with 5 elements. So we are always taking the group with 5 elements. And similarly here we also have the information we need. We know that in one group we have 0, 3, and 4, and in another group we have 1 and 2. And this is all we need. Now we are at index 1, so we are here. We know that this is the source. And we also know that this belongs to the group of 1 and 2. This means in this group we have 2 elements, and we can add the 5 elements on the right because we are always connecting the source with the 0. So 2 plus 5 is 7, so here we add a 7. And similarly, now we are looking at index 2. This means this is the source. 2 belongs to the group of 1 and 2. And we are also connecting these 2 with this node in the right graph. So this is also 7. Next, we are at index 3. So the source is this one. And we know that 3 belongs to the group of 0, 3, and 4. So we have 3 elements on the left side plus 5 elements on the right side, because we are always connecting the source with this one. So here we have 3 plus 5, and this is 8. So we put an 8 here. And finally, this is the source. This 4 belongs to the group of 0, 3, and 4, so we have 3 elements in this group, plus 5 elements on the right side, so here we put an 8. So now this is the final array, and this is what we need to return. Time complexity for this will be big O of n plus m, because we are doing only one breadth first search in this graph and another BFS on this graph. And space complexity will also be n plus m, because we are building adjacency lists for both graphs. So now let's go with the code, and hopefully you will get the idea. First, we need to build 2 adjacency lists. So we will create a function to do this. We'll call this build adj. This will take some edges, and in here we'll create adj. This equals a default dictionary, and we will set a default value for every key in this dictionary of an empty array. We do this like this in Python. And now for every a and b in edges, adjacency at a dot append b and adjacency at b dot append a. And finally we return this adjacency list. And with this function we can say adj1 adj2 equals build adj, and this will take edges 1 and build adj. This will take edges 2. Now we can say n equals length of edges 1 and m equals length of edges 2. Here we can build the breadth first search function. We can call this BFS, and this will take 2 arguments, a start node and an adjacency list. And we need a queue for every BFS, and we can use a deck in Python to pop elements from left. So we will use a deck. This has an array inside, and we will start with a tuple which will contain 3 values: the start node, a parity, and we'll use a 0 for even and 1 for add. So we will always start with 0 as the problem requires, and we'll use a parent to prevent cycles. We will start with a parent of -1. So just to be clear, this is node, parity, and parent. And now we can create 2 groups. One will be even and one will be add. This equals to set and set. And now while we have something in the queue, we can pop elements from the left. So queue.pop left, and this will give us 3 elements each time: node, a parity, and a parent. And if the parity is a 0, we add to even the current node. And if the parity is not 0, we add to the add elements the current node. And now for every neighbor in the adjacency list at the current node, if the current neighbor is different from the parent, here we'll create a new parity. This will be a 0 if the parity is currently 1, else it will be a 1. So if the parity is a 1, the new parity will be 0, and if the parity is a 0, the new parity will be a 1. And now we can add to the queue a new tuple with the current neighbor, the new parity, and the current node. And finally we return our two groups, even and add. So now we can use this function to run a BFS on the left graph, on the first graph, and another BFS on the second graph. So even 2 add 2 equals BFS starting from 0 with the second adjacency list, and even 1 add 1 equals BFS starting from 0 with the first adjacency list. And now the maximum in the second graph will be equal to the maximum between the length of even 2 and the length of add 2. And finally, the result is initially an array with 0 times n plus 1, and we will return this result. But here in between, for I in range n plus 1, if the current I is in the group of even 1, result at I equals the length of the group even 1 plus the maximum on the right graph, on the second graph. Else, result at I equals the length of add 1 plus the maximum on the second graph. So this is it for the code, and now let's submit this and see if it works. This works and it's efficient. So if you found this useful, please drop a like, subscribe, and see you in the next one. Bye bye.